Now, a spinner has sectors marked A, B, and C. The probability that the spinner will land on each letter is given by the table below. Everybody happy with that table below there, yeah? Now, it has to add to 1, so what's x? I'd say it's 0.35. How did I get that? 1 take away 0.5 take away 0.15. So the value of x is 0.35. If the spinner is spun 400 times, estimate the number of times the spinner lands on C. Well, it's 400 multiplied by 35%, or 0.35, and what you get? Huh? 140, yeah? Cool. Let's move on. Easy money there. 18. Carol has bought 3 dice. She suspects one of them is biased, landing 2 frequently on 1. Carol asks her sisters to test a die each. To make sure the test is fair, she doesn't say who is suspected die. Each sister rolls their dice repeatedly and records how many times they scored the number 1. Here are the results. 3, 8, and 27. Now, if you roll it 10 times, how many times should you get a 1? 1/6 of the time, which is roughly, anybody? 1.67 times, yeah? Roughly that. It's impossible to get that, isn't it? You either get it once or you get it twice. I think 3 is close enough to you. I think it's within the error. I think it's within the expected error. Okay. What about 50? What you would divide 50 by? And what happens when 50 divided by 1/6? Anybody just tell me in the calculator? Is it 8.3? Recurrent? 8.3 recurrent? 8 is pretty close, isn't it? I don't think you can get any closer. This dice is perfect. What about the next one? 100 multiplied by 1/6. And what you get? 16.6 reoccurring. 27 is far away from 16, isn't it? So what does that mean? You think Elena has the faulty dice. Okay? Yes, Mel. What's your chance of rolling 1? 1 in 6, yeah? Yes, sir.
I guess I just multiplied the number of trails. They all were 100.
Sorry, you did what?
So I just multiplied the number of trails for each person.
Yeah.
Until they were all 100. And then.
Oh, lovely. That's a cool way of doing it as well. So what they're going to do? What's 100? 100 divided by 6 is roughly 16. What Owen did was he multiplied both sides by 10. Now, there's a reason you're not allowed to do that. See, you can't assume that happens. Just because I roll 1 3 times in the first 10 doesn't mean I'm going to keep doing it over and over again. It's too early to tell. You know what I'm saying? It's a good idea. But with chance, you can't say it's going to behave the same way every 10 throws. So while it was a good idea, it's not the right idea. Sorry. So you got to do it like this. You got to go on the data you have, not imaginary data. Okay? Everybody cool with that? All right, let's keep going. 20. A die has faces numbered 1 to 6. Did I forget a question? What did I forget? Use the table above to estimate the probability of scoring 1 on the biased die. Alright, no bother. The biased one is the 27 out of 100, or yeah, should be around 16.6%. It's way too high. Okay. Now, 20. A die has faces 1 to 6. A die is biased so that number 6 will appear more often than each of the other numbers. Numbers 1 to 5 are equally likely to occur. The die was rolled 120 times, and note that the 6 appeared 450 times. Which statement is correct? Well, just give me a second. What's 450 divided by 1200? Anybody? Anybody got it? 3 over 8. Perfect. You have 3/8 chance of getting a 6. Would you agree with that? How much 8s are left? 5/8. 5/8 are divided amongst what numbers? Would you agree that the 5/8 is divided amongst numbers 1, 2, 3, 4, and 5? So that'll be 1/8, 1/8, 1/8, 1/8, 1/8. And what did we say 6 was again? And what happens when you add all those fractions together? 1. Yes. Yeah. Just give me a second. Probability of rolling the 5 is expected to be a 7th. No. The number 6 is expected 2 times as often as any other number. No, it's expected 3 times as amount as any other number. 1/8 versus 3/8. The number 6 is expected to appear 3 times as often as any other number. True. The probability of rolling an even number is expected to be equal to the probability of rolling an odd number. What's the probability of an even number, lads? 2, 4, and 6, which is 5 out of 8. Probability of rolling an odd number? 1, 3, and 5. Are they equal to each other? No. The only one that's correct is that one there. Restaurant. Okay. 500 cars, yeah? Alright, let's just do relative frequency first. What's 70 over 500? 7 over? Oh, we'll put it in decimal, why not? What is it in decimal? 0. What? 14, thank you. 100 over 500? 20%? Yeah. 45 over 500? Point what? 0.09? Yeah. 55? 0.0? 11? 140 over 500? What do you get there? 0.28. And finally, alright, what number goes here? Because it has to add up to 500. 90. That's because when you add downwards, they all have to add to 500. Is that okay? And what's 90 divided by 500? Huh? 0.18. Everybody cool so far? And what does this add up to? 1.0, because it's 100%. Alright, done. Done. What's a method for checking that the relative frequencies are all correct? Kieran, how do you check that all these numbers are correct? All the yellow numbers. And when you add them up, A equal 1, don't they? Go with that? What's the probability that the next car to pass the light is red? What? Well, according to this data, it will be 14%. Now, use the information to estimate the frequency of each color if 2,400 cars pass the lights in a full day. Or that's easy enough. You know, all you're going to do, see your percentages in yellow, just multiply them by 2,400. So it's going to be 2,400 times 0.14, 2,400 times 0.2. You get what I'm doing, don't you? If somebody just call me out the answers, that'd be awesome. First one. Yeah, next one. 480. 216. 264. 122. Can't be 432. Is it? Oh, sorry, I'm wrong. Sorry, 432. Yeah, next one. 672. And when you add all them together, you should get. Awesome. The data collected by student is not a random sample of cars passing through the day. Do you think that this makes your statements in 5 above reliable? Yeah, maybe there's a boy. Sorry, this is a very wish-washy English type answer. What you say is that a random sample would mean that you'd have equal chance of getting every color of car. You'd have just as much chance of getting a red car as you would a silver car. Humans are influenced. So do you know when you're on your road and you see all the other cars, like silver cars, black cars, navy cars, it's very few people that will say, "Oh, do you know, I'm going to get a lime green car." You tend to do what other people do. Stuff like fashion, haircuts. Surprise how humans imitate people, okay? So in this case, you can say that because we expect the rest of the cars are in the same area and we expect it to follow the same trends in taste. Do you get what I'm saying? So it's not a random sample. We expect it to be a biased sample where the people living in that area follow certain tastes. Is that okay? Great. And we're done.